Silicon is a semiconductor, which means its conducting properties can be tailored by introducing impurities to the crystal structure. Silicon has 4 electrons in its valence shell. This is the outermost orbit for electrons, and it determines many of the chemical properties of the atom. Atoms want 8 electrons in that shell, as this makes them very stable. So silicon readily forms covalent bonds with 4 neighbouring silicon atoms to gain those extra electrons. Now, if we introduce those impurities to this pure silicon crystal, we can change how it conducts the current. If we add phosphorus, which has 5 electrons in its valence shell, the extra electron is left free to roam the crystal structure. This extra electron makes the n-type negatively charged, which is where the name comes from. The p-type is positively charged because it is doped with boron, which has 3 electrons in its valence shell. This structure wants to gain its final electron, and will steal electrons from its neighbouring atoms. This creates a mobile positive charge, called a hole. The conductivity of the material has thus been increased, as we've increased the number of mobile charges. When we arrange n-type and p-type semiconductors like this, and attach terminals to each, we create the world's most prevalent transistor, the NPN transistor. The transistor works due to the interaction of those free electrons and holes at the n-type and p-type junction. Free electrons in the n-type will migrate over to fill those holes in the p-type. This creates a boundary layer called the depletion layer, which prevents more electrons passing through due to the negative charges repelling each other. But when a positive voltage is applied to the base, it negates the depletion layer and allows current to flow through, completing the circuit. As you can see, this is very similar to the function of the vacuum tube. So how exactly does this allow computers to perform all these complex functions that we see today? Let's look at a very basic example. Let's add 2 numbers together. First, we need to learn how numbers are represented in binary. That's the 1s and 0s that are used to store data. This is the number 15, which is the largest number you can represent with 4 bits. The first bit represents 1, the next 2, then 4, and finally 8. Added up, that equals 15. This pattern continues, with each successive bit representing double the previous, so we can add an additional bit if we want to count up to 31. Let's add 5 and 6 together. To do this, we want a circuit that will hold a 1 in this position when either are 1, and carry the 1 forward when both are 1. As you can see, this will give us the number 11. The simplest circuit that can do this is a half adder, which contains 2 types of logic gates. These are devices that can modify the binary code. They are built using transistors. The first is the XOR logic gate, which gives a 1 only when one of the inputs is 1. If both are 0 or 1, it gives a 0. The second logic gate is an AND gate, which gives a 0 for everything except when both inputs are 1. If we wire these logic gates like this, we create a half adder, which gives 2 outputs, our sum and our carry. This allows us to add our binary number 1 bit at a time. A more complicated circuit is needed to perform the calculation in one step. Modern computers can perform millions of these calculations per second, and they're still getting faster. The co-founder of Intel, Gordon E. Moore, noticed a trend in 1965 that the density of transistors on integrated circuits doubles every 2 years. That trend has held until very recently, but it is starting to slow down. One of the reasons for this is the less well known of Moore's predictions, Moore's second law, or Rock's law, which states that the cost of manufacturing these devices will double every 4 years. Intel made an announcement last year that the rate of advancement was slowing for these reasons. It's getting more and more difficult for chip manufacturers to shrink their product while maintaining profit. Another problem that transistors are facing is quantum tunneling. As these transistors get smaller, so do the barriers between different sections. The barriers between each section of the transistor are getting so thin that electrons can pass right through them. With no definitive successor to the silicon transistor lined up, this incredible period of growth over the last 50 years could plateau in the near future. Some want to harness quantum mechanics to perform calculations faster than any transistor ever could. Others want to decentralize computing power and create the so-called Internet of Things. Intel have said themselves that they plan to shift their focus from increases in speed to decreases in power consumption. One thing is for sure, the computer industry will have to redefine itself in the near future.